Morning, students. So last class we discussed about the classification of cables and the derivation of insulating resistance of a cable. Now we go for the capacitance of a single core cable. Capacitance of single core cable, dielectric stress in a single core cable, most economical conductor size in a cable, grading of cables, that is capacitance grading, inter-sheath grading, capacitance of three core cables, comparison of underground and overhead systems. So advantage and disadvantage of cables. These are all will be discussed in today's class. First, go for the capacitance of single core cable. As you discussed in the insulation resistance of a single core cable, that means a single core cable considered as equivalent to long coaxial cylinders. That means, so look at the figure, this one and this one. The conductor of the cable is inner cylinder, while the outer cylinder represented by a lead sheath. So this is the one cylinder and this is the another cylinder. That means conductor may be considered as a low cylinder, inner cylinder, and the lead sheath may be considered as a outer cylinder. Now the outer cylinder is represented by a lead sheath which is at earth potential. Look at the figure. Lead sheath may be considered as a earth potential. Let us consider a single core cable with a conductor diameter small d. Conductor diameter is small d. Whereas in derivation of insulating resistor, we are taking resistance of a, radius of a conductor small r1. Sheath radius is small r2, but here we are taking diameter. Conductor diameter small d and inner sheath diameter capital D. So let the charge per meter axial length of the cable be Q, capital Q coulombs, and epsilon be the permittivity of insulation material between core and lead sheath. Obviously, epsilon is epsilon naught and epsilon r. Epsilon naught value 4 pi into 10 power minus 7, whereas epsilon r is the relative permittivity of the insulation. Now let us consider a radius of small x meters, that means that is center of the conductor to P point. One with L meters. The surface area of the cylinder is 2 pi XL as usual on the insulation resistance. But 2 pi x into meter square, we are taken as 1 meter, that's why 2 pi x meter square. Now electrical flux density at a point P on a cylinder is dx is equal to charge Q by 2 pi x, charge by area. So that is dx is equal to Q by 2 pi x coulomb per meter square. And now we have to find out the flux density. Now electric field intensity. Intensity is nothing but, so density, ratio of density to permittivity is nothing but intensity. Electric field intensity Ex at a P point, Ex is equal to dx by epsilon. So dx means Q by 2 pi x epsilon, Q by 2 pi x epsilon naught epsilon r volts per meter. Now you have to determine the electric field flux density and then intensity. Now go for the work done. Work done in a moving of a positive unit charge from point P through a distance dx, small dx, in the direction of electric field Ex dx. Therefore, the work done in moving with a positive unit charge from conductor to sheath, that is taken as the integral part of that one. So V is equal to potential difference in V between the conductor and sheath. V is equal to integral small d by 2 to capital D by 2 Ex dx. That is equal to small d by 2 integral small d by 2 to capital D by 2 Q by 2 pi x epsilon naught epsilon r dx. So Q 2 pi epsilon naught epsilon r, the constant taken as a common factor, that is Q by 2 pi epsilon naught epsilon r and 1 by x log x. Applied the intervals, that is small d by 2 lower interval and capital D by 2 is the higher interval. Therefore, log capital D by 2 minus log of small d by 2. So log A minus log B is nothing but log A by B, that is equal to log capital D by 2 by small d by 2, 2 cancel. Therefore, log capital D by small d base E. So, potential difference between conductor and sheath V is equal to Q by 2 pi epsilon naught epsilon r log capital D by small d base E. Therefore, whenever we have to find out the potential difference between the conductor and sheath, now easily find out the capacitance. What is the capacitance definition? Is the ratio of Q by V, Q is equal to CV. So charge in a conductor is directly proportional to the potential difference across the conductor. Therefore, Q proportional to V, Q is equal to CV. Therefore, C is equal to Q by V. We know the V. So therefore, C is equal to Q by V. That is equal to Q by 2 pi epsilon naught log capital D by small d. So this 2 pi epsilon naught will go to the numerator, that is 2 pi q cancel, q pi epsilon naught r log capital D by small d farad per meter, right? Here small d conductor diameter, capital D inner sheath diameter, q charge per meter axial length of the cable, and epsilon r is the relative permittivity and permittivity is the epsilon naught. We know the epsilon naught value, that is 8.854 into 10 power minus 12. 2 pi into 8.854 into 10 power minus 12 epsilon r divided by, now log base E is converted into log base 10, that is equal to log base E is equal to 2.3 log base 10. So 2.303 log base 10 capital D by small d farad per meter. Now calculating with calculator all the constants, we are getting capacitance of a cable of a single core cable is, capacitance of single core cable is epsilon r by 41.4 log capital D by small d base 10 into 10 power minus 9 farad per meter. It is very important. So out of these two derivations, capacitance, insulation resistance of single core cable, capacitance of single core cable, both are important. Both are very important for B.Tech point of view. Now go for the dielectric stress in a single core cable. Under operating conditions, the insulation of a cable is subject to electrostatic stresses. That is nothing but electrostatic forces. We may call it as dielectric stresses. When our load increases, electrostatic stresses are increased. That means dielectric stresses are increased. The dielectric stress at any point in a cable is, in fact, the potential gradient at that point. That means dielectric stress is nothing but potential gradient for a particular point. Now let us consider a single core cable with a core diameter small d and a sheath diameter capital D. As provided in equation last derivation, the electric field intensity at point x, Ex is equal to Q by 2 pi epsilon naught r x, as per the last derivation, right? Directly you are taken. Electric field intensity is equal to Q by 2 pi epsilon naught r x volts per meter. By the definition, intensity is equal to the potential gradient. Therefore, potential gradient small g at a point x from the center of the cable is G is equal to Ex. Therefore, electric field intensity is nothing but potential gradient. Both are equal for a particular point, right? So therefore, Ex is nothing but G. G is nothing but potential gradient. So G is equal to Q by 2 pi epsilon r x volts per meter. So now we know the voltage potential difference between conductor and sheath. V is equal to Q by 2 pi epsilon r log d by d as per the last derivation. Therefore, from that V is equal to Q by 2 pi epsilon r log d by d, we get the Q is equal to 2 pi epsilon r V by log capital D by small d, right? Substitute taken as equation 2. substitute this charge equation in the potential gradient equation, that is substitute equation 2 in equation 1, we are getting G is equal to 2 pi epsilon naught epsilon naught V by log capital D by small d 2 pi epsilon naught epsilon naught x. 2 pi epsilon naught cancel to each other, therefore remaining term is potential gradient G is equal to V by x small x into log d by d base E volts per meter, taken as equation 3. That means from you can observe that, you can clearly notice that equation 3 gives the potential gradient of single core cable. Observe the potential gradient equation. The potential gradient is varied with inverse to that of distance x. Therefore, potential gradient will be maximum when x is minimum. When x is equal to small d by 2 or surface of the conductor, on the other hand, potential gradient will be minimum. So potential gradient will be maximum at the conductor surface. Potential gradient will be minimum at the lead sheath surface, right? So move on the top of the cable, potential gradient will be minimum. So center of the cable, potential gradient is maximum. So therefore, maximum potential gradient, that is x is equal to small d by 2. Substitute x is equal to small d by 2 in the above equation. G maximum is equal to 2V by small d into so log capital D by small d volts per meter. And the minimum gradient potential gradient will occur at the top of the surface of the cable, that is lead sheath. Put x is equal to capital D by 2. G minimum is equal to 2V by capital D log d by d base E volts per meter. Now, so G maximum by G minimum, divide these two equations. G maximum by G minimum is equal to, all are cancelled, and we are getting capital D by small d, that is G maximum by G minimum is equal to capital D by small d. The variation of stress in dielectric strength as shown in the next figure. It is clear that dielectric stress is maximum at the conductor surface and its value goes on decreasing as we are moving away from the conductor. It may be noted that maximum stress is an important consideration in the design of cable. If a cable is to be operated such a way that voltage, that maximum stress is 5 kV per millimeter, then the insulation unit must have dielectric strength at least 5 kV per millimeter. Otherwise, breakdown of cable may occur. Now, condition. What is the most economical conductor size in a cable? As you already shown that maximum stress in a cable occurs at the surface of the conductor. Minimum voltage occurs at the sheath or top of the cable, right? Therefore, safe working of the cable, dielectric strength of insulation should be more than the maximum stress. Now we know the G maximum value, 2V by small d log d by d volts per meter. For getting the maximum value, most economical conductor, you have to derive the above equation with respect to diameter of the conductor. Therefore, so derive the denominator and then equate into 0, that is enough. So small d by dd of d log capital D by d equal to 0, that is, so two terms is there, d and log d by d. So d, the derivative 1, therefore log d by d plus d into log d by d, that is d by d, 1 by d by d, and 1 by d derivative minus capital D by d square equal to 0. So log d by d, d square, this small d square cancel, capital D cancel, that is log d by d base E minus 1 equal to 0, log capital D by small d equal to 1, capital D by small d is equal to e power 1, that is equal to 2.718. So that is the condition, capital D by small d is equal to 2.718 is the most important bit for competition examination. Most economical conductor diameter small d, because conductor diameter is small d, right? Most economical conductor diameter small d is equal to capital D by 2.718. Now substitute this d value in the above equation. We are getting the G maximum value, that is 2V by D. G maximum value, that is equal to 2V by D volts per meter, right? So another important, so two derivations are important, and most economical conductor derivation important. Then and top most important topic for our B.Tech point of view is grading of a cables, right? Generally, as you discussed in the last minute, so electric stress is maximum at the conductor surface, and it will goes on decreasing, and it is having minimum value at the lead sheath, right? So that means electric stresses are not uniform throughout the cable, right? So to getting, otherwise to achieving uniform electric stresses in the dielectric of cable is nothing but grading of a cable. The definition of grading of cable is nothing but the process of achieving uniform electric stresses in the dielectric of a cable is known as grading of cable. Very, very important for 2 marks and also 10 marks also. It has already been shown that electric stresses in a single core cable has maximum value at the conductor surface and goes on decreasing as we move towards the sheath. The maximum voltage that can be safely applied to the cable depending upon the G maximum. For safe working voltage, we are utilizing dielectric strength of must be greater than the G maximum. If dielectric of high strength is used for a cable, it is useful only near the conductor where stress is maximum. So suppose as you move away from the conductor, the electrostatic stress decreases, so that the dielectric will be unnecessarily overshooting, overstrong. The unequal stress distribution in a cable is undesirable because of two reasons. Firstly, insulation greater thickness is required, which may increase the cable size. Secondly, it may lead to breakdown of insulation, right? Because of unequal distribution of electric stress, insulation having greater thickness such that cable size increases, and a breakdown may occur in the insulation. Because of these two reasons, to overcome these two disadvantages, it is necessary to have a uniform electric stress or uniform stress distribution in a cable. This can be achieved by the distribution of stress in such a way that its value increases in outer layer of the dielectric. That is nothing but grading of cable. There are two main methods of grading of cables. First one, capacitance grading. Second one, Inter-Sheath grading, right? So what is a grading of cable? The process of achieving uniform electric stress in the dielectric of a cable is nothing but grading of cable. Why? What is the necessity to prepare the grading of cable is nothing but because of unequal stresses, insulation size increases and the insulation breakdown may occur. To overcome these two, so grading of cable is necessary. Here two methods of grading methods are there, capacitance grading and Inter-Sheath grading. So for the first one, capacitance grading, the process of achieving uniformity in dielectric stress by using layers of different dielectric is known as capacitance grading. We are utilizing so many dielectrics, epsilon 1, epsilon 2, epsilon 3, like that. In capacitance grading, the homogeneous dielectric is replaced by a composite dielectric. Generally, we are utilizing homogeneous dielectric. Now it replaced with a composite dielectric. The composite dielectric consists of various layers of dielectrics in such a manner the relative permittivities epsilon r for epsilon is inversely proportional to the distance of the center. Under such conditions, the value of potential gradient at any point in the dielectric is constant. and independent object is distance. In other words, dielectric stress in a cable is same everywhere and the grading is ideal one. However, ideal grading is requires use of infinite number of dielectrics. It is an impossible task. In practical cases, we are utilizing only 2 or 3 dielectrics in the decreasing of order of permittivity. So we are decreasing order of permittivity. The dielectric of highest permittivity being used in near the core only. Voltage is high in the core. That's why relative permittivity of core is high, and then move on decreasing relative permittivities. Capacitance grading can be explained beautifully by referring the following figure. There are 3 dielectrics of outer diameter small d1, small d2, capital D, and the relative permittivities of epsilon 1, epsilon 2, epsilon 3 respectively. If the permittivities are such that epsilon 1 is greater than epsilon 2 is greater than epsilon 3 respectively, and the 3 dielectrics are worked at the same maximum stresses, therefore 1 by epsilon 1 d1, why? Because distance is same. 1 by epsilon 1 d equal to 1 by epsilon 2 d1 equal to 1 by epsilon 3 d2. From that, epsilon 1 d is equal to epsilon 2 d1 epsilon equal to epsilon 3 d2. Now we are getting potential difference across the inner layer. As usual, V1 is equal to integral small d by 2 small d1 by 2 g dx. We know the g potential grade q by 2 pi epsilon naught epsilon r x. By integrating with inner and outer limits, we are getting q by 2 pi epsilon naught epsilon log basically d1 by d. So this is nothing but g maximum by 2 d log d1 by d. Similarly, for second layer, potential across second layer, V2 is equal to G maximum by 2 D1 log D2 by D1. Similarly, potential across top layer, V3, G maximum by 2 D2 log D by small d2. Now, total potential difference between core and lead sheet, that is V1 plus V2 plus V3, that is equal to G maximum by 2 is the common factor. Small d log D1 by D plus D1 log D2 by D1 plus D2 log capital D by D2. For a cable may having this derivation is for composite dielectric. Suppose if cable had a homogeneous dielectric, then for the same values of D1 capital D and G maximum, the permissible potential difference between the earth sheath would have been V dash. Suppose it is a homogeneous and this is composite. V dash is equal to G maximum by 2 small d log capital D by small d. Obviously, V greater than V dash for a given dimension of the cable. Grading of cable can be worked at a greater potential, right? Main disadvantage of this method is there are a few high-grade dielectric for reasonable cost whose permittivity varies with a required range. Now, this is the another one is Inter-Sheath grading. In this method of cable grading, a homogeneous dielectric is used. Capacitance grading, composite dielectric is used. Coming to the Inter-Sheath grading, we are utilizing Inter-Sheath grading, right? But it is divided into various layers by placing metallic intersheath between the core and lead sheath. Intersheaths are held at a suitable potentials which are in between the core potential and earth potential. So this arrangement may improve the voltage distribution in the dielectric of a cable, and consequently more uniform potential gradient is obtained by this method only. That's why this is more important. Sometimes they ask a question like this, explain the Inter-Sheath grading briefly, or sometimes explain the grading of cables, like that they ask a question. Now go for the, look at the diagram. Let us consider a cable of core diameter small d and outer lead sheath diameter capital D. Suppose two inter-sheath of diameter having D1 and small d2 are inserted into the homogeneous dielectric medium, and it is maintained a fixed potential, right? Let V1, V2 and V3 respectively with the voltage between core and intersheath 1, between intersheath 1 and intersheath 2, between intersheath 2 and lead sheath. As their definition of potential difference between the inner and outer layer of intersheath, therefore a sheath will be treated as a homogeneous single core. Therefore, as usual, we know that maximum stress will occur in the conductor. G1 maximum V1 by D by 2 log D1 by D. Similarly, G2 maximum V2 by small d1 by 2 log d2 by d1. G3 maximum V3 by small d2 by 2 log capital D by d2. Since the dielectric is homogeneous, the maximum stress in each layer is same. Maximum homogeneous, because of homogeneous, stresses are all same. So G1 maximum is equal to G2 maximum is equal to G3 maximum, that is equal to G maximum. Say from that V1 by D by 2 log D1 by D is equal to V2 by D1 by 2 log D2 by D, that is equal to V3 by D2 by 2 log capital D by D2. So to cancel to each other, as the cable behaves like a 3 capacitors in series, therefore all the potential are in phase. Voltage between the conductor and earthed lead sheath is V is equal to V1 plus V2 plus V3. Even though it is more important because of homogeneous dielectric, and it is having 3 disadvantages. So mixing of sheath potentials, that is the basic disadvantage. Secondly, intersheaths are likely to be damaged during the transportation. Thirdly, there are considerable losses in the intersheath due to charging currents. For these reasons, intersheath gating is rarely used. Rarely, because of 3 disadvantages, it is rarely used. Last topic, capacitance of a 3-core cable, very important, very important for 3 purpose, and competition exam purpose also it is very important. Capacitance of a cable system is much more important than the overhead system, because in the cable conductors are never to each other, nearer to each other, and to the earthed sheath. They are separated by a dielectric permittivity much greater than the of air, right? That's why it is much more important. Figure shows the capacitance in 3-core belted cable used for 3-phase system. Since potential difference exists between pairs of conductors and between each conductor and lead sheath, electrostatic fields are set up in the cable as shown in figure. These are the figure 1 will show the electrostatic stresses developed in the 3-core cable. These electrostatic fields gives rise to core-to-core capacitance, that is CC, and conduct to earth capacitance CE as shown in figure 2. Because of these electric stresses between core and lead sheath, core it will act as a core capacitance, that is CC, and core and lead sheath, core and earth may act as a core earth capacitance, that is CE. Now 3 CC are in delta connection, right? Whereas 3 CE are in star connection. Look at the figure clearly. 3 CC connections, core to core capacitance may be acted as a delta connection, and 3 core to earth capacitance may be acted as a star connection. Now CC, 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 CE, 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 clearly. So core to core capacitance formed as a delta, and core to earth capacitance may be formed as a star. Now the lay of a belted cable make it region able to assume equal each CC and each CE. That means 3 delta connected capacitance CC shown in the figure individually, 3 earth to capacitance are shown in here. Now this 3 delta connected core to core capacitance may be converted into star That is nothing but C equivalent is equal to 3 cc, C equivalent is equal to 3 cc, C equivalent is equal to 3 cc. Now delta may be converted into star, that means so 3 cc, 3 cc, 3 cc. Now it can be easily shown that equivalent star capacitance C equivalent is equal to 3 times of delta capacitance Cc, that is C equivalent is equal to 3 Cc. Now the system capacitance shown in figure, it may reduce the equivalent circuit shown in figure. C equivalent and CE, C equivalent and C both are in star, both are in parallel. C equivalent and CE, C equivalent and CE, C equivalent and CE. Now two capacitance are parallel is nothing but both are in series, in parallel is nothing but adding to each other. C neutral is equal to CE plus C equivalent, CE plus C equivalent, CE plus C equivalent. Now therefore Cn, CE plus C equivalent. What about C equivalent? 3 Cc. So capacitance of neutral is Cn is equal to CE core to earth capacitance plus 3 times of the core to core capacitance. If the voltage is phase voltage, then charging current IC is equal to V phase by capacitive reactance, that is V phase by XC, that is 1 by omega C, that is 1 by 2 pi FC. Therefore 2 pi F V phase Cn, 2 pi F V phase Cn means Cc plus 3 Cc. Now I have to measurement individually. What about CE equation and what about Cc equation? So we know that the first measurement, 3 cores are bunched together and the capacitance is measured between the bunched core and the sheath. The bunching eliminates all the 3 capacitance Cc, leaving the 3 capacitance Ce in parallel. Therefore, C1 is equal to 3 times of the Ce. So, Ce is equal to C1 by 3. By knowing this C1 value, the value of Ce will be determined. Similarly, C2, for second measurement, 2 cores are bunched with the sheath and capacitance is measured between them and the third and then the third core. Therefore, that may gives the 2 Cc plus Ce. If C2 is measured capacitance, then C2 is equal to 2 Cc plus Ce. We know the values of Ce and C2, then we can determine the Cc. Therefore, C3 is equal to Ce plus Cc by 2, Cc by 2, that is equal to 1 by 2 Ce plus 3 Ce. We know that Ce plus 3 Cc is nothing but Cn. So, C3 is equal to 1 by 2 Cn. Right? Like that, we have to determine the capacitance values 3 core cable. Now, lastly, comparison between underground and overhead systems. For public safety, overhead system is less safe, underground is more safe. As per initial cost, overhead system is less expensive and underground system is more expensive. For occurrence of fault, fault occurred frequently in overhead system, very rarely occurred in the cables. Appearance, it gives shabby look, but coming to the underground system, it gives a good appearance. Flexibility, it is more, overhead system is more flexible, and it is not a flexible one. Location of fault, fault point can easily located, fault point cannot easily located. Repair is very easy, but repair is somewhat complicated. Working voltage, it may be working up to 400 kV, so it can work only up to 60 kV, that is pressurized cables or screened cables. Lightning, thunder, more chances of being subject to lightning in overhead system. There is no lightning, little chances, very little chances in the cables. Supply interruption, more chances of supply interruption. So in underground cable, it is very little chances of supply interruption. Accidents, more chances for accidents in overhead system. So very less chances for accidents. Interference with communication systems. In overhead system, it is more, that is interfere with the communication system, that is telephonic lines. There is no interference with communication system. Insulation cost is very less in overhead system, but insulation is very high because we are utilizing various wrapping of high grade tapes, that is lead sheath also provided. Erection cost, small maintenance cost, that is repair cost, but erection cost is high if voltage cable is quite high. Very uses means overhead system is used for a long distance transmission system, whereas in large charging current on the high voltage limits use of long distance transmission. Long distance we are not using for cables. What are the advantage and disadvantage of cables? Main advantage is nothing but better general appearance, good appearance, less chances to damage to the storms and lightning, low maintenance cost, less chances of faults, small voltage drop. All these are the features of cables. And main disadvantage is greater installation cost and installation problem as voltage increases. This is about cables. Now we discuss about the introduction to cables, construction and insulating materials in the first video. In second video we discuss about classification and insulation resistance. Now this class we discuss about the remaining part of the cable unit. So now from this class, so theory of cable is complete. Next classes we discuss about the numerical problems on insulation resistance, insulation capacitance, 3-core cable and dielectric medium, and also grading of cables, Inter-Sheath grading or capacitance grading, right? Thank you one and all. To see this video, please subscribe DBS Talks, right? Out of total 50 units, that is underground cables, the most important topics are classification of first insulating materials, classification of cables, derivation of insulation resistance, derivation of single core capacitance, right? 3-core cables, grading of cables. They are all very important. Most grading of cables, 3-core cable, insulation resistance, insulation capacitance of single core cable. These 4 are very important, and some problems discussed later classes, right? Thank you one and all. To see this video, please subscribe DBS Talks.